the main idea for this session is using the artificial intelligence for medical image processing, but we can use the same methods for many different other technologies. Let's start with some definitions and some applications. In this session, I'm trying to start with some definitions that we have heard much, but maybe no, no way, it's not moving. Okay. Where else? Yes. One things that I want to explain first is that artificial intelligence is not going to remove humans from technology. This is one question that we hear every session that we have, that are you going to exchange the artificial intelligence for humans? But this is not the idea, this is not the goal of using artificial intelligence. It comes to help us. It's not coming to change us. It's not coming to remove us. But there are some concerns about that. But hopefully we are thinking of cooperation between human and machines here. So what we are now going to talk about is how humans can use machines to help them improve their systems and how to ease their systems. So let's begin with the definition of artificial intelligence. What is artificial intelligence actually? Please interrupt me anytime that you have questions and ask your questions anytime that you want. I'm more than happy to answer your questions. This slide is based on the book, a famous book that Professor Stuart Russell wrote. It's tell us that there is not one definition, but actually more than one. You can see here four different definitions of the artificial intelligence, and most of them are very old. You can see that some definitions are here from 1978, but actually the first definition of artificial intelligence is back to 1950s and 1960s, when the computers first was born. But it is long time that the scientists are thinking about this method. For example, a group of scientists thinks that artificial intelligence means that you can build a system that can act like a human. For example, you can see here Kurzweil in 1990 says, artificial intelligence is the art of creating machines that perform functions that require intelligence when performed by human or by people. Or for example, another group of scientists think if we can build a system that can think like a human, this system can be an artificial intelligence or AI. For example, you can see here that Bellman says the automation of activities that we associated with human thinking, activities such as decision making, problem solving, and learning, these are meaning of the artificial intelligence. In a state of these groups of definitions, we have two other groups that they say human is not the base or the source of the intelligence. We must think about the rationality. So if we can build a system that think rationally, this system can be an artificial intelligence. How can we build a system that think rationally? It is very important. This returns back to the logic. You know, the logic is built more than 2000 years ago in Greece. So when the, um, the early scientists built their um, first rule of logic, they never think that 2000 years later, people come back to that and use that to build a system based on their very simple rules of logic to make it an artificial intelligence. And finally, the fourth definition backs to the group of scientists like Professor Russell and Professor Nielsen, that they says that the system can be an artificial intelligence system if it can act rationally. To make it happen, we need to make something that we call it an intelligent agent. So this group of people believes to the agent-based systems. So we have four different definitions from four different groups of people, and it is very important that we use which one of these systems. If you believe to the um, acts rationally, so you need to make agent, artificial agent. But if you believe to this definition that is here, think like human, so you need to understand what the system can um, think like a human. Normally, we don't have CPU, RAM, or other hardware or software devices in our brain. So how human think? You know that human thinks based on the very simple system based on neurons. This is a diagram of a neuron. As you can see, the neuron has some parts. The parts is nucleus or the center of the neuron, and it has some input parts that we call them dendrites, and there is one very long output of the neuron, we call it axon. Every dendrite has a connection with some axons. This connection is called synapses. So when you are thinking about something, what is happening in your mind? It is a very difficult question, and many physiologists and biologists think about that, and finally they found that when you are thinking and you are learning something, your system change this synapses. So some axons will remove from this dendrite and will rejoin to other dendrites. So this is what makes us to think, and this is the source for our decision-making system. And it is very, very interesting. I can explain it a bit more in next slides. But let me return back to some previous slides that I jumped from them. If you believe to other systems, if you believe to the agent-based systems, then you must think of other methodology for learning. So it was better than I define learning first. What is learning? Learning means that you change your action after you experience some experiences. Actually, the bad experiences change your behavior more than the good experiences. If you do some things and you get punishment for that, you will not going to do that again normally. But if you don't get any punishment for that action, so you can repeat it more and more and more. So what learning says is that if you experience something and get an punishment or bad results of that action, you will change your action. So if you want to have a learning system, we must do that like that. This is a diagram that Professor Russell proposed for agent-based system which has learning facility. As you can see here, this system, which is this big square here, has in action with an environment which is actually much bigger than this agent, but here it's shown very small. We have some inputs that can get to the system by sensors, and we have some output that we can make it in the environment by actuators. What will happen is normally in the agent-based system, we have a performance element which has this job to get the sensors input and make it to the actuator's output. So it says, for example, if the temperature is low and you feel cold, just close window or put more clothes. So this is the normal performance elements that we have, and we need to make it in every artificial intelligence system. But to be a learning system, this system needs more elements. For example, we need a learning element. What these learning elements do, as you can see here, this learning element just says change. And it is the word that you can hear is very much from different people in the world. For example, when Obama has campaigned for presidency, his word was change. And also there was many people other that say that we want change, but maybe their change was different from Obama's change. So if your system wants to be a learning system, someone must to say that you must change your behavior. This learning element cannot see what is happening. So we need another part, we call it critic. This critic see and check everything that the sensors give to the performance element. So it can check it with the performance standard and see if it is okay or something is wrong. If something is wrong, it sends a feedback to the learning element, and then learning element inform the performance element that you must change your behavior. Otherwise, you will be punished. This loop will happen more and more and more, and finally your system can learn that the good behavior is bad, and otherwise it will be punished again. Also, there are other parts. For example, another part is a problem generator. Then it is. I'm not going about to talk about it right now, but maybe later we can return back to this. Okay. So if we want to define the artificial intelligence, we need to choose one of these definitions. But what is machine learning? Machine learning is part of the artificial intelligence systems. If your system have the learning facility, it can have um, the learning element, so it can change its behavior. So it is part of the machine learning. But if it is not a learning element, or it doesn't have a learning element, it is not part of machine learning. We have many artificial intelligence systems that are not a learning system. So if they do something wrong, they will repeat it again and again and again. But still they are artificial intelligence systems because they can do it like a human. Part of the machine learning systems are systems based on the neural network system. Neural network systems are the systems that are simulated then human neurons and try to do or act like a human when human thinks. So it's returned back to the second definition that we talked about it previously. And part of the neural network systems are deep learning systems. Deep learning systems are systems that have many, many neurons, not just 2 or 3 layers, but many layers, and each layer has different jobs. So this diagram shows that the artificial intelligence is the subset, or is the superset of all of these, and machine learning is a subset of the artificial intelligence. Neural network is a subset of machine learning, and deep learning is a subset of the neural networks. We have other systems too. We have some systems called expert systems. This group of systems are very interesting because they are built based on the knowledge of the human. These groups, the left side groups, have some information injected to them by humans. So it's called expert systems because expert inject the information to these systems. If there is any question, I'm happy to answer. Otherwise, we can move more. Okay.
I have a question, sorry.
Okay, yes, please.
Wouldn't there be like a hybrid system between both of them? Like, sometimes we use like Neuro Fuzzy, which is an expert system and a neural network as well.
We can have these 2 parts, but these 2 parts are just a sequential parts. So you do some parts, some actions using neural network, and then the output comes outside and you feed it to the other part. But they cannot fuse together. You don't have any fusion between these different systems because these systems are really different. For example, when you have an artificial intelligence system, you need to get some features for your problem. I explain it by a very simple example very soon. But when you're using a neural network system, this system itself choose the features. So there are difficulties to feed these human selected features to the machine selected features. Actually, there are some solutions for that, but it is not very common. I myself, with one of my PhD students, wrote an article about the deep learning system based on the combination of the features. Some part of features comes from outside, and some part of the features was generated by the deep learning system itself. But it is not a very common and very simple system. So normally you have these different systems separate, but you can have these systems sequentially when one part do some jobs and give the results to the other part, and other part use or process this and pass it to the next stage, and like that. You can see in this slide a form of this. In the left side, you can see the one neuron. As you can see, we model it by a very simple mathematical model. We say that, okay, in a neuron, you have some dendrites. These dendrites are input for our neuron. So we get some x's like x1, x2 to xn as a input to the neuron. Also, we have one output for the neuron, which is the axon of this neuron. So you put it here as a y and say, okay, the output of this neuron is y, but there are more than this here. What will happen when the inputs come and gather here in the middle of the nucleus? Let me see if I can write something. Okay. Okay. Explain it by words here. What will happen in the neuron is when an input comes to the nucleus, it will wait here until all the amount of the inputs comes to a threshold. So when each neurons get the specific amount of the ions at the nucleus, then it can send the output to the axon. We call it a neuron get triggered or fired. So when neuron fired, the output comes to the axon. Before that, you don't have any output in the axon. So this neuron is off. So we need a function to simulate that behavior. The function here can be a very simple function, as you can see, like this function. We call it a step function. When the input are less than this threshold, the output is 0. But as soon as the output reaches this threshold, the input reaches these thresholds, then the neuron's output becomes 1. This step function is very good and very simple, but actually there is some difficulties for it. For example, this function is not differentiable, so we have some difficulties for calculation. Instead of this step function, we use some different functions like a sigmoid function, which is similar to this step function with this formula, but it is much, much better because you can get derivative of this function, and its derivative is very simple. And so you can have very good calculation and much simpler calculations than the calculation for the previous one. Or you can have some combination of these two, like Relu function. You can see that this function says, okay, if your input is less than this threshold, the output will be 0. But as soon as the inputs gather and come more than this threshold, your output is as much as the input. So instead of it being the same for all the values, the value will be increased. And it is, again, a very simple formula and have a very good mathematical characteristics that we use it in our discussion maybe later. So if I return back to this slide, you can see that we model our human neuron by a very simple bond. So how this system can learn something, why we say this system is a learning system. Is there any idea between audience? We'll be happy if you have an interactive session.
I think it's in the parameters. So by tuning the parameters, we change the outputs of the network.
Yes, you are right, but which parameter do you mean?
The weights.
Yes, that's right. It's okay. That's the key answer for this question. You see that we have many synapses here. Actually, we have 10 power 11 neuron in the human brain, and each neuron has 10 power 4 synapses to the other neurons. So we want to put this into the action. So we add some weights like W1, W2 to Wm, which says each of these inputs are stronger or weaker than others. So when X1 is a very strong input, we multiply it by W1, which is a very big value. But when X2 is a very weak input, we multiply it by W2, which is a very low value, or even it can be a negative value. It means that when the X2 increases, it not help this neuron to get fired, but it prevent it from get the output. So we have different range of the weights. Normally they are from -infinity to +infinity. So if the weights change, your system will learn. How? Let me say one very simple example. Think about that we have a system that wants to find the difference between apples and oranges. For doing that, we need to have some features for these two fruits. You may say that, okay, let's think about their color and their weights. Apples are very small, so their weights are less, but they are red, so their color is more than the oranges that they are less color, but they are bigger than apples, so their weights are more. So to doing that, if Dariush helps me, I want to draw something here. See how.
Yes,
Okay.
there is annotation on top.
Yes, I find it just now. Thank you. So we have two axes, one for W or weights and one for C or colors. Apples are light, but their color are red, so they normally are here. Oranges are bigger and heavier, but their color are orange, not red. So if we think of X1 as a first feature here and X2 as a color here, so you can have an neuron with two inputs, X1 and X2. What will happen is that the X1 will multiply by its own weight, which is W1, and X2 by its own weight, which is W2, and they will be multiplied and summed here to make the net, which is this X1 W1 plus X2 W2. Okay. So what will happen if I make it an equation and say X1 W1 X2 W2 is equal 0? You know that this is the definition of a line. So this neuron can draw a line for us that is here, and this line can discriminate between apples and oranges. If you put some values for X1 and X2, if the value for this formula be positive, you have apples. If this formula returns a negative, it is an oranges. And if it is 0, you have the points on the discriminant line. This is what a neuron can do for us. And what will happen if the neuron do the wrong thing and have this line? So you need to change the weights toward that part that get the better results. So if you have a different weights, you will have a different lines. By using this method, you can change the weights of this neuron, and these changes help you to improve your accuracy, and this means that this system can learn from their mistakes. If you give it some fruit and say, what is this fruit? And say, okay, it is apple, but actually it was an orange, you punish this system. It means that you force it to change its weights. And when it changes its weights, it can draw another line and another line and another line until you get happy and say, okay, it's fine now, and all the fruits are correctly classified. So this is the actual learning method for the neural network, for a neuron. So when we have one neuron, our system can learn from that. Okay, let me return back to my slides. But the problem is all the systems are not as easy as this system that I explained. What about a system that have fruits in this form? Some of them are here, and some of them are here. You cannot use any line to discriminate between these two different points because they are not linearly separable. So one neuron cannot solve this problem. Instead of that, we need a neural network system, which is a system based on several neurons. You have some neurons here, some neurons in the next stage, some neurons in another stage, until you get the outputs. So in that system, you have two different layers for the system, and it starts of the neural network philosophy, which happens in 1970 when some people come and says, okay, your very simple system, as you explained here, cannot solve very simple problem like XOR. You know, in the logic, we have XOR gates, which are like this when it's are 0 and 1. Both inputs are 0. It is 1. It is 0. When both are 1, it is 0. But when one of them is 0 and the other one is 1, it is 1. This system is not linearly separable, so then a neuron cannot solve this problem. XOR is one of the simplest gates in the logic gates. So when your neuron cannot solve this, this system is useless. It was the words that make the neural network history to stop for more than 30 years. And nobody could think about the neural networks, even, and they knew that it can be very useful if they use it by using the idea of the neural networks, but they couldn't call it neural network. They use it something like adaptive filtering or something like that. So after 30 years, some people came and say, okay, one neuron cannot solve this problem, but we can have two lines. Each of these lines can be happened by one of these neurons, and finally you can add another neuron on top of them, and you can have this output. Very simple. So the neural network idea. What about the different outputs here? Can anyone have any idea why we have many outputs here? In the previous one, we just have one output, but here we have different outputs, y1, y2, until yn. Why are these so many outputs?
I think if it's not a decision between two classes, then we need more outputs.
That's right, exactly. If you want to discriminate between different fruits, apples, oranges, bananas, and other fruits, then one output is not useful. You need to have more outputs, and each output can tell you that how similar is this uh, fruit to each of these um, predefined fruits that you say. For example, if you put the first neuron for the oranges and it says, okay, this fruit that you showed me is 0.7 orange. The other neuron says, okay, it is 0.33 apple. The other one says, okay, it is 0.9 banana. And the other one says it is 0.1, for example, say something. I don't know, mandarin. Okay. Then you can check all the outputs and say, okay, because this one is the biggest among all the outputs, it is more similar to be this fruit. For example, if it was orange, or banana, than to be an apple or orange or mandarin. So each neuron separately decide how similar is this neuron to this input is to the pre-designed value for that neuron. Now there comes another question: how these neurons knew which fruit is apple and which fruit is orange or like that? Tessa, do you want to explain it?
Yeah, I think probably due to the weights that we associate for classification purposes, and then as long as that weight supports that classification, then we prioritize the output. And in this way, we can say, as you mentioned, 0.9 is associated for the banana in this case. So in this case, we would see from point of the classification purposes that all the inputs with the weights are supporting to this such decision. However, there are plenty of methods, as you mentioned here, deep learning one, but there are other methods also that could compare this, or perhaps we might have some sort of multi-classifier fusion purposes.
Yes, that's right. I asked this question to explain the difference between the supervised learning and unsupervised learning. As you explained, these neurons need someone to tell them if their output are correct or they have mistakes. So for doing that, we need some data that we call it training data. In the training data, we have the information for X1 and X2. Also, we know the label for this class. We know that this fruit is orange. And also for other one like this, we know the X1, X2, and also we know that this one is apple. So these training data has a class label plus the input features. But when you want to examine this system, you use it some unknown data which you don't know, or your system does not know that it is apple or orange. You just give it the x1 and x2, but you don't say if it is apple or orange, and your system have to explain it and say if it is orange or apple. And if it was correct, you get it a point, and if it was not correct, you punish it and you reduce its points. So by using this system, you have an supervised learning. Supervised learning are very common in classification, like in neural networks, like BP, backpropagation neural networks that we explain later, and some other systems like support vector machines, Bayesian classifiers, KNN, and other methods that we call them classifiers. But there is another type of the learning that we call it unsupervised learning. In unsupervised learning, you don't have training data. You just have raw data. These raw data don't have any class label. So you have plenty of fruits that you don't know them. I remember when I was in Australia, one day I saw Chinese people, I think, selling bananas, but they don't know what the name of the fruit, so they put a sign over that banana and says this big red, big yellow fruit is $1 for each kilo. So this unsupervised system is like that. When you don't have the, let me go to the next slide to have a more space. Yeah. Oh. So you have many fruits, you scale them, so you have their weights, their colors, but you don't know which one is which. So the only thing that you can do is to group them by their similarity. Say, okay, these fruits are similar to each other, these groups are similar to each other, and these groups are similar to each other. You don't have their class label, you don't know their name, but you can still cluster these groups by putting them in one basket, just to say that they are in the same basket because they are very similar. The unsupervised learning comes from this idea. Unsupervised learning is very simple, and it is a bit faster than the classification. So normally we use it for pre-processing in our process, and later we explain it more about that. I was going to tell more about this idea. Let me say which slide I'm on. Okay, for example, we can see that these very simple systems can be used for finding the, for example, cancer tumors in medical imaging. This paper is very good paper for classifying these applications, artificial intelligence, machine learning for medical imaging, a technology review. If you check this paper, it explains different methods, and in the next session, I'm going to explain each part and use this system to explain how this machine learning system or deep learning system on other artificial intelligence systems, as you can see in the right side of this slide, which are like random forest or support vector machines, are act, and which one is better. As you can see here, these words may use in different years, less or more. For example, in 2020, the convolutional neural networks, CNNs, which is part of the deep learning systems, are very popular now. But in 2010, the most popular one was support vector machine. Why it happens and why this change happens in the technology, this is what we are going to talk about in the next session. And also I'm going to explain some, yes, this is the parts that I draw them by hand. So this is, for example, a method for decision trees or random forests. The decision tree is one of the artificial intelligence system. It tries to divide the system based on the value of each features. For example, if I draw the diagram again here, if your data are these data, the decision tree says, okay, if you use the first feature, x1, it can divide these two to different groups on this value, for example, A or A1. But sometimes you have some other data from oranges here as well. So this is not enough. So you need to draw another line for x2, which is here. And say, okay, if you divide then on x2, you can have apples in one part and oranges in these two parts. This is what happened in this diagram as well. Back to that slide. Yeah, it says, okay, check x1 or f1 with x value. If it is less than x, then come here and check the second feature. If it is greater than x, okay, it's enough, it's classified to apples, for example. And it happened more and more and more. You can do that for patients in hospital, and you can classify them based on if they are COVID-19 patients or they are not COVID-19 patients. It is interesting that in some systems that we use more than one classifier, we call them ensemble of classifiers. For example, here you can see that instead of we have one decision tree, we have different trees. So it call it the random forest, which means that there are more than one classifier for this system. And in this system, you have different classifier that they say different results. Maybe one of them say it is apple, the other one say it is orange. Then what we can do now? There are many methods here to combine the result of different classifiers. One of them is just a simple voting. If you have 7 classifiers and 4 of them says it is apple, so it is apple. Maybe they are wrong, but the majority of the classifiers say it is apple. And if you use the majority voting, the result will be that. Another method is based on of the voting of the specialists. So you have different classifiers. Some of them have more weights. So if you gather all the votes, then you multiply their votes to their weights and then use the result. So the classifier with more weights can have more effects on the final results. And there are many other systems. For example, we have majority voting. We have another way that each classifier are specialized for special cases. For example, in a hospital, maybe you have a classifier to classify only diabetic patients, and the other one is just for the heart disease patients, and the other one for example, the dementia or other diseases. So each classifier has a specialty. So when you get the results, try to use this specialty to understand which part say the correct results more. This is another diagram that compare between the completeness of supervision and the time of the supervision. So for example, when you have an unsupervised learning system, it is an really unsupervised. So the completeness of supervision is absent here. But in the supervised learning, it is completely supervised. In between, we have some different systems that we call them semi-supervised systems that are very interesting, because if you want to learn the system with the supervised learning, you need a lot of training data, but it is difficult. For example, if you want to classify between the COVID-19 patients, you need a doctor or physicist to see all the patients, for example, X-ray, and mark them or annotate them for you before you feed it to the system. And it is very difficult and very expensive. Instead of that, if you have only a few results for the patients and some people that are not sick, then you feed it to the system, and system itself learn it and change it to the other or expand it for the other data. This system can be called a semi-supervised learning, or even we can call it self-supervised learning as well. Very different group of learning, which is called reinforcement learning. is very popular these days in the reinforcement learning. The system try to punish and say that punish is get gift, for example, to itself based on the results that it get from the system. So there are very different systems in the artificial intelligence, and just another one, or the last one that is in here, is a transform or transfer learning. In transfer learning, you have trained a system based on the information of one patient or one person. For example, when you talk to your mobile phone and it answers you, your Google Assistant or Siri answers you, so the system can understand what you are saying. It is trained based on your voice. But what will happen if your wife or your brother come and talk to the system? It cannot understand it correctly, but it can transfer your model of talking to his or her model of talking. So we call it the transfer learning. It is much faster than starting from scratch and learning from the very beginning of data. So we have many systems that we need to do, and as you can see here in this slide, sometimes we have systems that are combined between these systems. For example, some parts as a pre-processing parts are unsupervised, and their job is to get the feature from data or feature extracting or feature selection. And the other part is to predict the model or get the results to us. And deep learning is normally here because this part, feature selection and feature extraction, is part of deep learning, and it doesn't need any feature extraction and feature learning separately. We will talk about some examples of this in the medical image processing later. As for example, this is a GAN system or generative system, which is a very simple and very interesting one, but you may have see some result of it in deep fake, for example, when you can see, for example, your grandparents are talking or singing for you, but actually these are a fake video is generated by this generative system. This system has two parts. One part is a generative part, and the other part is the okay. This generative part has this job to make the fake images and send it to discriminative part. Yeah. Then discriminative part have to or has to find the difference between the real and the fake image and check and answer if it is the real one or the fake one. And if this feedback says, okay, I find it, this was fake, it is not real, it returns back to the generative image and it makes it another image and another image. And this loop happens more and more and more until you find some images and videos that are very difficult to check and find that it is a fake video or fake images.
I
I
have a
want
question.
to,
Sorry.
yes, please.
I have a two-part question. In terms of machine maintenance, we have something called, I think you heard of it, like digital twinning. So I'm thinking, what kind of system do you use for digital twinning? because you need to
Sorry,
update
I didn't understand. Digital.
twinning. Digital twinning is like what Amazon and these guys, you know, they build a system based on some features that information they get from you, and then that keeps updating the system depending on your age, your location, and things like that.
Uh-huh.
So,
Uh-huh. Yes. If I am right, I think you're talking about some systems like recommender systems. That in these systems, the system try to recommend you some options. For example, when you go to Amazon and buy some books, next time it offer you some books that are very similar to those subjects that you have bought before. Or when you go to Facebook and find one of your friends, old friends, and add it to your networks, it recommends some more people that are your friends as well. But how can this system find this similarity between these people? Yes, these kind of systems that we call recommender systems are part of our decision support system that help us to decide better and more accurate for our systems. Maybe later, I don't have the slides for that part, but we can have added for the next session. I will write it down and we'll talk about the decision support systems in the next session.
My other question has to do
Yes.
with like, you know, such a like an example of evolving systems, which you know, if it creates a feature that it has not seen before, you know, like can create a new cluster based on the new information. I see that, you know, especially in machine monitoring, when the machine is aging, so there is new feature that appears that have not appeared before. And I'm just wondering what kind of system would that be considered?
Yes, this part that you said, it is very important and very useful because normally when we have problems, let me use my fingers to show you that. If we have classes like these two groups of fingers, very complex to each other, very near to each other, there is no way to find a decision boundary between them. But if you transfer it to the higher dimension space, then you can have these two ants different in different dimension, very simple separatable. So what will happen is your system try to generate new features, not just select among the other features or previous features. It tries to generate new features, and these new features have this ability that can a classifier solve the problem very simple, much simple than before. For example, when you use a SVM support vector machine, and the problem is non-linearly separable, they normally use a kernel method, which is the same as what I explained here. They increase the dimensionality of the space. So in a state of a two-dimensional space, we transfer our data to three-dimensional space. And in the three-dimensional space, it is very simple to divide between them and make these two groups linearly separable. So some features that will generated here are not actually the true features from the data. They are generated. So after that, if you return it back, then you can see some effects that are very simple and very interesting. For example, when you find some features or some new features for the face, and if you change these features, then you return it back to the actual image, you can see that, okay, the face of this person, excuse me, the face of this person is changed, and for example, maybe get aged, or from man is changed to a woman, or it may be combined between the two images of two different persons. For example, a very simple one is using the PCA, principal component analysis. In principal component analysis, you have a dimensionality of the same as the dimensionality of your features, but these new features are very interesting because they are linearly generated from the previous one, but they are orthogonal to each other. So they are less similar between these new features. So when you change or move from one axis in the new features, you can see different effective on the faces. For example, if you combine the new features of two persons together, you can see a face which is very similar to both of them. And in other systems, for example, on RBF systems, you can make it in the higher dimensional space as well. I don't know if I answer your question or not.
Yeah, yes, you did. Yeah, and I saw like similar thing in um, neurofuzzy, where the evolving system, it creates a new cluster. Like, if you add, like, let's say, an aging formula for the machine, because the machine after a while does not give you the same responses. So it has to create a new feature to accommodate all of that changes.
I just want to use the remaining time just to introduce three books that are very interesting and very useful. For example, the first one is Digital Image Processing for Medical Applications, which is very useful. In the left-hand side, you can see the content of this book. For example, part 1 is Introduction to Image Processing. Part 2 is the fundamental concept of image processing. Part 3, image analysis. And part 4, medical application and ongoing development. This book is mostly about the image processing. But the other book is which is Medical Imaging, Artificial Intelligence, Image Recognition, and Machine Learning Techniques, which you can see here is based on the medical parts as well. For example, the first chapter is a novel stacked model ensemble for improved TB detection in the chest radiology and so on. So if you are more like me to read books about the medical imaging, so this book is more interesting for you. And the other one is the artificial intelligence in medical imaging, which is the combine of these two. You can see some parts like big data in medicine, or quality, regularity, and ethical issues in this book as well. There are some books just for deep learning and computer vision. One of the very useful or most useful one is this one that I find very good, and I commend it for you. Okay, I think my time is over for this session, and for the next session, I hope that we can start to see some applications, as Darius said at the beginning of the session, we are trying to give some idea to the people that how can they use these techniques for their problems, not only for the medical applications, for other applications too. So if you want to use this information, come and join us in the next session too. Thank you very much for being with me, and I'm happy to hear your feedbacks and questions.
Thank you, Dr.
Thank you.
Rimpu.
You're welcome.
Dr. Rimpu, just, yeah, go on, Dariush.
No, please go ahead, Dr. Mushir.
Oh, yeah. That was great, actually. You reviewed the fundamental issues regarding of the concept of artificial intelligence and deep learning. Just one thing which I'm a bit concerned regarding of the majority voting that you mentioned for the classification, if you could bring that slide. Usually, it's a question that it depends on the nature of decision making. If the decision making is very aggressive, say, for example, when we are detecting the smokes, so the smoke detectors for firefighting, we have to make a decision very fast. So our decision will be based on majority voting. But however, when we have a conservative decision making, in that sense, then we are still waiting for all the classifier to make decision, and then we use the concept of consensus rather than or versus of majority voting. So this is the question that probably depends on the system, that to how sensitive we are to that system. As I told you, for firefighting or fire alarms, majority voting is the solution for releasing the people or actually helping, assisting the people. But however, in some senses, if we are considering very conservative point of view, usually they use the consensus, means all the classes should be considered in the final decision making. Have you faced with such this issue, by the way?
Yes, we have a mathematical condition for using the majority voting, and actually not one, but three. But the most important one is that you can have a majority voting only if you believe that at least each of these voters have accuracy more than a chance. For example, if the system is a combination of 100 classifiers, that their accuracy is less than, for example, 10%. So when you do the majority voting, your final result will not be good at all. But instead of that, you have to improve each of these classifiers, or we call them learners, to get the accuracy more than 50%. If they get more than 50%, then you can improve the results by the majority voting. Otherwise, combining these, I can say, not accurate learners, you get the worst results, and it is logical and it is rational, because when most of them say wrong, when you get the majority of these results, the final results would not be true or correct.
Yes, yes, you are right.
And
you are right. Yeah.
this is not the only condition. There are three conditions. I can recommend you the book written by Professor Theodoridis, which was our guest in the previous conference that we had in Iran as a virtual conference in April. and he had a 1 hour talk. He was the keynote speaker of us, and he's the writer of the very famous books in statistical pattern recognition and statistical machine learning. If you want, I can give you the name and information about these books. In his book, he explained that for get the better results for ensemble of classifiers, you need to have 3 conditions, and the most important one was one that I explained.
Thanks very much indeed. Hopefully for
Alright.
next time, if you share that reference, they will be very happy to follow you. Thanks very much
Sure.
indeed.
You're welcome. I think Behzad has another question as well.
No, I just wanted to thank you for the presentation. Great slides. Very interesting way of describing this concepts. I had seen some of it, but I still learned something new today. Thank you.
You're welcome. It is difficult to explain the technical information for the audiences from different level of information. So I tried to explain as much as possible and as simple as possible. I don't want to enter in the very mathematical parts that, but as well, I want to give you some information. As you said, you had this information before, but maybe these examples that I try to find and say here help you and other people to understand and get more and deep information of that. For the next session, I want everybody think about the simple question, as I showed in the previous slides. We have neural networks that has several layers, and each layers can help us to get the better results. But actually, mathematically, it is shown that you only need 2 layers to do most of the current problems, to solve most of the current problems. But as you can see in the deep learning system, we have many layers. So the question that in the next session, I will try to explain it first is why deep learning is so important and why we try to use more than 2 layers, while mathematically we just need only 2 layers for solving most of the problems. Again, thank you very much, and sorry for the delay and getting more time.
Thanks very much indeed. Thanks very much.
You're
Thank
welcome.
you very much, Dr. Hussain, for your great presentation. If anybody has any questions, no more questions. We will resume this session next week and in the same time on Sunday next week at 11 o'clock in EDT time. I shared the Telegram channel link, and I wonder if you would like to be in touch with us, please join our Telegram channel, which is the link is shared in the chat box. Anybody has any questions or anything? Saeed, are you going to say anything?
I just want to thank you for your presentation.
You're welcome. Thank you very much. Thank you to have you all here. And I will be more than happy to get any feedback from this session. Thanks a lot and have a good weekend. Bye for now. Goodbye.
See you next week.
Thank
Bye.
you. See you.
Bye.
Bye now.
Bye.
Bye. Thanks.